Imagine a heart the size of a three-story house, just pounding away with the power of thousands of cars. That's what we're talking about with the main engine of a massive container ship. It's an absolute marvel of engineering, but it's also a ticking time bomb, constantly generating a crazy amount of heat. So how do its guardians keep it from literally melting down? Down in the scorching heat of an engine room, you've got one major enemy: temperature. Every single moving part, every drop of oil, all the cooling water, it's all in a constant battle against overheating. And if that engine gets a fever, it doesn't just get sick, it can lead to a catastrophic failure miles and miles from any shore. So how do you actually solve this? I mean, think about it. How are you supposed to take the temperature of something that huge, that powerful, and that incredibly hot? You can't just walk up and stick a thermometer in it, right? The challenge is way more complex than that. And the answer, well, it's pretty brilliant, actually. You don't measure the heat directly. Instead, you use a physical property that changes with the heat. You find a material that can feel the temperature and then report back what it's sensing. You basically teach a piece of metal to think. And that brings us to the real unsung hero of our story. The little device that does all this thinking is based on one fundamental principle of physics: electrical resistance. It's called a Resistance Temperature Detector, or RTD for short, and it does exactly what its name says. It's a special type of sensor built from a material whose electrical resistance, its opposition to the flow of electricity, changes in a very precise and predictable way as it gets hotter or colder. Okay, so here's the cool part. How does this actually work? Think of it like this. Electrons are runners on a track. When the metal is cold, that track is wide open, totally clear. But as the temperature rises, the metal's atoms start vibrating like crazy. It's like someone is suddenly throwing hurdles all over the track, making it way harder for those electron runners to get through. That difficulty, that restriction, that's the increase in resistance. And by measuring that resistance, we can figure out the temperature with incredible accuracy. But, you can't just use any old piece of metal for this. To be the brain of an engine's safety system, you need the absolute best material for the job. You need, well, the platinum standard. And in this case, that's not just a saying, it's literal. The most common and trusted RTD out there in the marine world is called the PT100. The PT stands for platinum, and the 100 means it has exactly 100 ohms of resistance at 0 degrees Celsius. That's the benchmark everyone uses. So why platinum? I mean, look at these properties. It's just the perfect candidate. First off, it's incredibly stable, so its readings don't just drift over time. Plus, its resistance changes in this almost perfectly straight line with temperature, which makes all the calculations super simple and accurate. It's also tough as nails. It resists corrosion and has a super high melting point. Both are absolutely essential for a harsh engine room. And this chart really lays out the trade-offs, doesn't it? Sure, you could use nickel or copper to save a few bucks, but with nickel, the readings aren't as linear, and copper just can't handle the really high temperatures. When you're talking about protecting a multi-million-dollar engine, the accuracy and stability you get from platinum are worth every single penny. No question. Okay, so we know what it's made of, but how these sensors are actually built is just as critical, because, different jobs are going to need different designs. You basically have two main types. On one hand, you've got the original champ, the wire-wound RTD. This is where a tiny platinum wire is carefully wrapped around a ceramic core. It's the king of accuracy, but it's more expensive. And then you have the modern challenger, the thin-film RTD. For this one, a microscopic layer of platinum is just deposited onto a ceramic chip. It's cheaper, smaller, and reacts to temperature changes a lot faster. That's why you see it so often in modern engines. So let's just recap the big wins here for RTDs. The most important things, really, are its incredible accuracy and its excellent stability. That means you can trust its readings day in and day out, which makes it absolutely perfect for the continuous, critical monitoring that an engine needs. But hey, nothing's perfect, right? RTDs are generally more expensive and a bit slower to react than their main rival, which is called a thermocouple. That's just another type of temperature sensor. And those super accurate wire-wound ones, they can be a little sensitive to heavy vibration. It's all about picking the right tool for the job. Okay, so let's get back to that massive engine room. We've met our hero, the RTD. Now let's see exactly where it stands guard. And these aren't just random spots, These are the engine's vital signs. We're talking about the main bearings, where these huge forces are grinding away,
the lube oil that keeps metal from destroying metal, the cooling water that's basically the engine's lifeblood. An RTD is stationed at every single one of these critical points, acting like a silent, vigilant guardian.
And here's the thing, they're not just fancy thermometers. They are literally the nerve endings of the entire ship's safety system. They are the very first to feel when something is going wrong and the first to sound the alarm.
And this is the chain reaction that saves the day. 1. A bearing starts to overheat. The RTD detects it instantly. 2. It zaps an electrical signal to the engine control room. 3. An alarm starts blaring, getting the crew's attention. And 4. If things are really critical, the system automatically starts to slow down or even shut down the engine to prevent a total meltdown. All of this happens in just moments.
So when you boil it all down, the job of this one tiny sensor comes down to 3 massive things: preventing overheating, protecting the engine, and keeping it running efficiently. And this technology isn't just on giant ships. A version of it is probably in the oven in your kitchen right now, making sure your food cooks at the right temperature. Which leaves us with one final thought. This humble, hidden sensor is a guardian in so many parts of our lives. What happens on that ship, or even in your home, the day it stops thinking?